Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is A Gentle Introduction to Surface Areas. As always, please be an active learner as you watch this video. In this section, we're going to apply double integrals to the problem of computing areas of surfaces. Now, we actually have done this once before for a very special type of surface, a surface of revolution. That was in Calc 2. But here we're going to compute the area of a surface with equation z equal f of xy, the graph of a function of two variables. And we will revisit this yet again in this course when we talk about the surface areas of more general surfaces called parametric surfaces. So think about this as being an intermediate step. So let S be a surface with equation z equal f of xy, where f has continuous partial derivatives. So it is a nice surface, and that's the blue picture that you see up here. So we want to be working to get the surface area of S. Now, for simplicity, we're going to assume that f of xy is greater than 0, as you see here, and the domain is a rectangle. So that means that the domain down here, the whole domain, the whole domain is this rectangle. Now we divide the rectangle D into smaller rectangles called Rij, with the area being delta x, delta y, as you can see in the picture. If then xi, yi is the corner of this rectangle, Rij, that's closest to the origin. So there is the origin, and there is this point, xi, yj. Then we're going to let P, which is up here, be the point Pij that's directly above that point. And again, we're being very precise so you can see that we're not double counting, and so on and so forth. All right, so now we've established this xi, comma, yj, and Pij up here. Now what we're going to do is we're going to be considering the portion of the tangent plane that is going through that point. And so we're taking this little pink post-it note kind of up here, and that's going to be a parallelogram by construction. We're starting with this point. We're going to consider the parallelogram where this side is parallel or lives in the xz plane, and this other vector is again well, that one's parallel to this one, so the other vector, the other side, is going to live in the yz plane. So we're going to construct those parallelograms. That's what we're doing. Okay. So the tangent plane to S at Pij is an approximation of S there, and so the area of that little piece of the tangent plane, that parallelogram that lies directly above Rij, is an approximation to the area, and that is delta Sij of the part of S that lies directly above Rij. So if we add these all up, we get an approximation to the total area of S, and the approximation improves as the number of rectangles increases. Therefore, the surface area can be this Riemann sum. Now, this is going to be, the limit is m and n both go to infinity. So now we're going to focus on what does this look like. Okay, so let's blow it up a bit, and we're now focusing on the post-it note. So here you can see the post-it note with the parallelogram the way I told you I would construct it. And we know then from actually the work we did on vectors that the magnitude of this parallelogram, let me say it a different way. The area of this parallelogram is going to be the magnitude of the absolute value of the cross product of this vector A and this vector B. So we're going to write what A is. Remember that A lives in the IK plane, and B, remember, lies in the JK plane. So this is A and this is B. And so we're going to compute the magnitude of this to get the area, which is this delta Tij. So we're going to first do the cross product of these two vectors. So we do the cross product. Now note we have 0 here and 0 here because of the way we define the sides of that parallelogram. So when we compute this determinant and simplify, what we get is and notice that we have delta x and delta y are a common factor, so we can factor those out and we can call those delta A. And then when we simplify what we have inside, this is what we have. So we have minus f sub x, x sub I, y sub I in the I direction, minus f sub y in the j direction, plus k. And that's 1 times k times that. So when we take the magnitude of this, what will happen is the magnitude will have the delta A is a scalar, but the magnitude of this is going to be the square root of these components squared. So now we have figured out what this is. So we're going to say that A of s is equal to that double sum, but now we have that this is going to be the square root of the absolute value of fx at xi yj whole squared, same thing for f sub y whole squared, plus 1 because the component here is 1. And now what we're going to do is we're going to take this limit. And the limit then becomes this, and this is in fact the surface area as a double integral. Now here you have it writing what f sub x and f sub y are. Down here you say z was equal to f of xy. So this is in terms of z, and this is in terms of this, and you should please note the similarity between this function and the one that we studied way back in Calc 1. Let's do a problem. So here you define the surface area of the part of the surface z equal x squared plus 2y that lies above the triangular region T in the xy plane, and the triangular region has vertices 0, 0, 1, 0, and 1, 1. You know what to do. Let's see how you did. We have to draw a picture of this. So this is the picture that we have, and we're going to integrate dy first. That means we fix x. So we draw this. So the y variable goes from 0 up to x. So using the definition, then a is equal to the integral over this domain D, which really was just this triangle here. The partial with respect to x is 2x. The partial with respect to y is 2. And I add 1, I do the arithmetic, and I get this. And I'm going to integrate with respect to y first. That means x is a constant, so I just get x times that constant, because the bottom limit was 0. And then I'm integrating this with respect to x now from 0 to 1. And I'll do a u substitution here, plug in the numbers, and I will get 1 over 12 times the quantity 27 minus 5 root 5. That's the exact answer. That's the answer that I'm going to want you to give. Don't give me an approximation to that. And so that's the way you'll do the calculation without even calculators. Here's another problem for us to try. Find the area of the part of the paraboloid z equal x squared plus y squared that lies under the plane z equal 9. You know what to do. Let's see how you did. Okay, now the plane intersects the paraboloid in the circle x squared plus y squared is equal to 9 and z equal 9. And so the surface we're getting is the surface area of this blue thing, but when I project down, I see that my domain, in fact, is the disk D with center at the origin and radius of 3, because I got that from this equation right here. So we're going to use our formula then. So the surface area is going to be the double integral over d of the square root of 1 plus partial with respect to x squared, partial with respect to y squared, square root of all that, dA. I take the partials, I have 2x and 2y respectively, and I square them and I get this. Now, so this is the integral representing the area. But as we know from previous studies, this is much better done using polar coordinates. So we're going to say that x squared plus y squared is going to be r squared, and dA becomes, you remember, r dr d theta. So we integrate with respect to r first, getting this, and then we integrate with respect to theta, getting this. We plug in the numbers and we get pi over 6, parentheses, 37 times the square root of 37 minus 1. Make sure you can do calculations like this and make sure you verify these calculations. Again, I'm going to expect you to give me exact answers. Let's do one more example. Find the area of the surface Z equal xy that lies within the cylinder x squared plus y squared equals 1. You know what to do. Let's see how you did. There's the statement of the problem again. It's within this cylinder. That means the projection D is, again, the unit circle x squared plus y squared equals 1. And we use our formula with the partials of x, partials with respect to y, and 1. And in this case, the partial with respect to x is going to be y, and the partial with respect to y is going to be x. So I get this. And again, glancing at this, we see, oh, this is going to be much easier done using polar coordinates. So x squared plus y squared is r squared. dA becomes r dr d theta. And I go from r being 0 to 1. And then theta goes from 0 to 2 pi to pick up all of d. So this is our expression. We evaluate this. We integrate first with respect to r, getting this. We plug in our values of 0 and 1. And then we integrate again with respect to theta. And our answer is 2 pi over 3, parentheses, 2 square root of 2 minus 1, end of parentheses. Again, that's the exact answer. That's what I expect you to be able to do. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.